On January 18th, 2026, at 18 hours 9 minutes Coordinated Universal Time, active region 4341 on the surface of the Sun produced an X-class 1.9 solar flare. 8 minutes later, the electromagnetic pulse reached Earth. Shortwave communication in the illuminated hemisphere went silent. This was only the beginning. The flare was accompanied by a coronal mass ejection, CME, which the LASCO coronagraph cameras aboard the Soho Observatory recorded as a full halo. A full halo means one thing: the ejection is heading straight for us. Initial ESA models estimated the cloud speed at approximately 1,400 kilometers per second. But when the shockwave front reached near-Earth space 25 hours later, recalculation gave a completely different number: 1,700 kilometers per second. The cloud was moving significantly faster than predicted. Write in the comments where you are watching us from, and we continue. On January 19th, the flux of high-energy protons in near-Earth space began to rise rapidly. First, the sensors of the GOES-19 satellite recorded a moderate level, STWO, then a strong one, S3, and at 18 hours 10 minutes UTC, the flux of protons with energies above 10 megaelectron-volts exceeded 10,000 particles per steradian per second per square centimeter. This is the S4 threshold, severe on the NOAA scale, a threshold that had not been reached for 23 years. The NOAA Space Weather Prediction Center issued an emergency notice. There was one phrase in the text of the bulletin that made space weather specialists around the world read it twice. The intensity level exceeds the values recorded during the Halloween storms of October 2003. Those storms still remain the benchmark for extreme space weather in modern observational history. And the January event of 2026 turned out to be more powerful. SWPC immediately notified airlines, the FAA, NASA, FEMA, and power grid operators through NERC. Polar flight routes found themselves in a zone of increased radiation risk. High-frequency communication in the polar regions ceased operation completely. Satellites in geostationary orbit, which means navigation, communication, meteorology, entered a zone of increased danger. And then the CME shockwave itself arrived at Earth. At 19 hours 38 minutes UTC on January 19th, the geomagnetic situation abruptly collapsed to the G4 level, an extreme storm. ESA issued a statement that the event has the potential to impact power grids, satellite operations, navigation systems, and the workload of astronauts in orbit. That night, the aurora was seen in Alabama, in Northern California, in northern Italy. And a photographer from the Brazilian city of Cambará do Sul captured something that almost never happens in these latitudes: a faint purple glow on the southern horizon, inside the zone of the South Atlantic anomaly, where Earth's magnetic field is weakened so much that even the rules of auroras stop working. All this occurred within a solar cycle that 7 years ago, an international panel of NASA and NOAA experts called probably weak. Out of more than 100 forecasts published between 1983 and 2024, only 4 turned out to be even approximately correct. The Sun refused to follow the script that had been written for it. 4 correct forecasts out of over 100 is not a modeling error. This is a systemic failure of an entire discipline. And to understand why the January event of 2026 has significance that goes far beyond a single storm, one needs to see the scale of how much reality diverged from expectations. In December 2019, the International Solar Cycle Prediction Panel, a joint structure of NOAA, NASA, and ISES, published the official consensus forecast for Solar Cycle 25. According to it, the cycle was supposed to reach its maximum with a peak smooth sunspot number of about 115 around July 2025. The panel assessed the cycle as comparable to the previous one, 24, which was the weakest in the last 100 years. Some of the forecasts presented to the expert council went even further. Some models indicated the possibility of a slow slide into a state similar to the Maunder minimum, an era of the 17th century when sunspots practically disappeared for decades and canals froze in Europe. Reality began to refute these calculations almost immediately. By January 2023, the activity of Cycle 25 exceeded the metrics of Cycle 24 at a comparable stage by 12% in terms of the daily number of spots. The sun was picking up steam faster than any of the baseline scenarios allowed. By December 2023, NOAA was forced to issue a radically revised forecast. The peak was now expected between January and October 2024, with a maximum number of spots ranging from 137 to 173. This is not an adjustment. This is an admission that the original model described a different star. On October 15, 2024, representatives of NASA, NOAA, and the panel officially announced that the sun had entered its maximum phase. By that moment, the observed smoothed sunspot number had already reached 157 in August 2024 and was outside the upper limit of even the revised forecast. Here it is important to stop and understand what this gap means in practice. Solar cycle forecasts are not an abstract academic task. Based on them, the lifespan of satellites in low orbit is calculated because solar activity heats the upper atmosphere and increases aerodynamic drag. Based on them, space missions are planned. Based on them, power grid operators assess the risks of geomagnetically induced currents, the very currents that in March 1989 blacked out the entire power grid of the Canadian province of Quebec in 90 seconds, leaving 6 million people without electricity. When the forecast says weak cycle, all infrastructure preparation is calibrated for a weak cycle. But the cycle turned out not to be weak. F. Value Foxon, an interdisciplinary researcher from the University of Texas at Austin, analyzed more than 100 published forecasts for Cycle 25 and found that only 4 of them correctly identified the peak parameters. Partly, the problem is a lack of data. The number of sunspots has been systematically measured for only 24 full cycles, and the radio flux at a wavelength of 10.7 centimeters for only 7. This is categorically insufficient for validating models, let alone for training machine learning algorithms. But there is another side. Cycle 25 did not just turn out to be stronger than expected, it continued to produce powerful events even after it was formally supposed to begin fading. The first months of 2026 brought a series of X-flares of such frequency and intensity that it caught off guard even those who had already accepted the revised numbers. And the January spore storm became not the culmination, but only the first act. 12 days after the radiation storm of January 19th broke the record of the Halloween storms, the sun showed that this was indeed only the first act. On February 1st, active region 4366 began a series of eruptions that in 4 days rewrote the statistics of the entire cycle. At 12:34 UTC on February 1st, NASA's Solar Dynamics Observatory, SDO, recorded an X-class 1.0 flare. Powerful, but in the context of the current maximum, ordinary. SDO's cameras recorded it in the 171 angstrom range, an ultraviolet channel that highlights hot plasma material in the solar corona. 11.5 hours later, at 23 hours 59 minutes UTC on the same day, the same region produced an X-class 8.1 flare. By some estimates, the intensity at the peak reached X-class 8.3. The discrepancy is due to differences in calibration methodology between different monitoring stations. In any case, it was the strongest flare recorded in 2026 and one of the most powerful in the last 2 decades. SDO captured the event in the combined 171 and 131 angstrom channel, a mix of spectral ranges that highlights different structures of the solar corona. The images show a bright flash in the upper part of the solar disk. Region 4366 at that moment was in a geo-effective position, directed almost exactly at Earth. Then followed a double blow. A few hours later, already on February 2nd, the same region produced 2 more flares, X-class 2.8 and X-class 1.6. Earth's ionosphere, which had not had time to recover after the first impulse, received 2 consecutive X-ray blows. High-frequency communication for maritime and aviation channels was disrupted again. And on February 4th, the active region produced another eruption, an X-class LOGO 4.2 flare, the peak of which occurred at 7 hours 13 minutes Eastern Time. It caused an R3 level radio blackout over Africa and Europe and entered the top 20 strongest flares recorded since 1996. 4 X-class flares in 4 days. A 5th one 3 days later, all from the same active region. To understand why this is unusual, one needs to understand the mechanics. A solar flare is an explosive release of magnetic energy stored in an active region. Magnetic field lines in the area of sunspots twist, intertwine, and reach a state of instability. When the tension exceeds the limit, magnetic reconnection occurs. The energy stored in the magnetic field is converted in minutes into radiation, ranging from X-ray to radio wavelengths, into streams of accelerated particles, and, in the case of the most powerful events, into a coronal mass ejection. Flares are classified by the peak flux of X-ray radiation in the range from 1 to 8 angstroms, classes A, B, C, M, and X, where each subsequent class means a tenfold increase in power. X class is the upper limit of the scale. Inside the class, a numerical index refines the intensity. X class 1 is powerful. X class 8 is territory where consequences of a planetary scale begin. Region 4366 demonstrated increasing magnetic complexity for several days before the start of the series. The NOAA Space Weather Prediction Center raised the classification of the region, but even after the upgrade, models did not predict a series of such density. When a single active region produces several X flares in a row, it indicates a continuous supply of magnetic energy from beneath the photosphere. Convective flows continue to feed the region faster than it manages to discharge. The region was not just exploding, it was recharging. Region 4366 was recharging, and on Earth, the consequences of each new discharge superimposed on one another, and system after system entered a mode for which they had prepared in theory, but which in practice they had not encountered for more than 2 decades. The most visible effect is the auroras. During the January G4 storm, the auroral oval expanded far beyond the usual polar latitudes. The northern lights were recorded in the states of Washington, Michigan, Maine, in the United Kingdom, in northern Italy. In the southern hemisphere, the aurora was observed over parts of Australia and New Zealand. But one observation is worth a separate conversation. Photographer Egon Filter was in the city of Cambará do Sul in the south of Brazil, 29 degrees south latitude. He was watching the southern part of the sky when a faint purple glow appeared on the horizon. He managed to take several pictures before the glow vanished. It lasted a matter of minutes. Cambará do Sul is located inside the zone that geophysicists call the South Atlantic Anomaly, a vast region over South America and the southern part of the Atlantic Ocean where Earth's magnetic field is abnormally weakened. The anomaly was first identified back in the 19th century. It arises due to peculiarities in the behavior of Earth's liquid outer core. In the region under the South Atlantic, magnetic field lines, which under normal conditions should emerge from the core in the southern hemisphere, behave in the opposite way. They go back into the core. The result is a local weakening of the magnetic shield, which has very specific practical consequences. Satellites flying over this zone receive increased doses of radiation. The Hubble telescope does not collect data when passing through the anomaly. Astronauts on the ISS do not go on extravehicular activity over this region. It is a zone that engineers unofficially call the Bermuda Triangle of space. And now in this zone where the magnetic field is already weakened, during the most powerful radiation storm in 23 years, a glow was recorded that should not occur in these coordinates. Specialists from the spaceweather.com portal noted that the glow could be a so-called stable auroral red arc, SAR arc, a diffuse band that forms when energy from the magnetosphere's ring current leaks into the upper atmosphere. SAR arcs have been observed at low latitudes during strong storms, but their appearance inside the South Atlantic anomaly is an observation that does not fit into standard models of auroral distribution. And here appears the context that makes this observation even more alarming. Data from the European Space Agency's SWARM mission, published in the journal Physics of the Earth and Planetary Interiors, show that the South Atlantic anomaly does not just exist, it is growing. Between 2014 and 2025, the area of the anomaly expanded steadily, but starting from 2020, a section of the Atlantic southwest of Africa began to weaken even faster. The anomaly is not just increasing, it is splitting into 2 separate lobes and slowly shifting westward. In 11 years of swarm observations, the area of the weakened field has grown by almost half the area of continental Europe. Professor of geomagnetism Chris Finley from the Technical University of Denmark, the lead author of the study, explained, "Usually, magnetic field lines in the southern hemisphere are directed upward, away from the core. But under the South Atlantic anomaly, regions of reverse polarity have been discovered, where the field goes back into the core. One of these regions is migrating westward, toward Africa. When the planet's magnetic shield weakens in a specific zone and the Sun at that moment operates at a power that no main model predicted, the coincidence of these two factors creates a situation that no space weather textbook describes yet." No textbook describes this situation yet, but that does not mean we do not have a historical precedent allowing us to assess where the next step on this scale might lead. A precedent exists. It is 167 years old. On September 1st, 1859, British astronomer Richard Carrington observed a group of large sunspots through a telescope. Suddenly, a bright white glow flashed in the region of the spots, a phenomenon that no one had documented before. Carrington sketched what he saw. 17 hours later, and not 3 to 4 days later, as with a typical CME, the shock wave reached Earth. The magnetosphere was compressed to the limit. Auroras were observed in the tropics, in Colombia, Cuba, Hawaii. Telegraph operators in North America and Europe found that their devices continued to transmit messages after the batteries were disconnected. The currents induced by the storm in the telegraph wires were sufficient for the equipment to work. Sparks flew from the contacts of the devices. Paper tapes caught fire. In 1859, the planet's entire electrical infrastructure was the telegraph. Today, it is power grids spanning continents, satellite constellations on which navigation, communication, and meteorology depend, aviation, financial systems, supply chains. In 2013, Lloyd's of London, together with the research company Atmospheric and Environmental Research, published a risk assessment of a Carrington-level solar storm for the North American power grid. The upper limit of damage is $2.6 trillion. The scenario assumes 20 to 40 million people without electricity for a period ranging from 16 days to 2 years. The greatest risk is concentrated along the Atlantic corridor between Washington and New York in the Midwest and along the Gulf of Mexico coast. The mechanism of vulnerability is simple. Geomagnetically induced currents, GIC, occur when rapid changes in Earth's magnetic field during a storm induce electrical currents in long conductors. Long power lines work as antennas for these currents. GICs penetrate transformers, causing overheating of windings, saturation of the magnetic core, and in the worst-case scenario, irreversible damage. Replacing a high-voltage transformer takes months. Spare ones in warehouses are usually not available. They are manufactured to order. The Lloyd's report noted that the cost of installing blocking capacitors on the 1,000 most vulnerable transformers in the United States would be approximately $100 million. After the Quebec blackout of 1989, Canada invested around 1.2 billion Canadian dollars in protecting the Hydro-Quebec grid. American investments in similar strengthening were significantly more modest. And here is another context that superimposes on the picture. In March 2026, the crash metric, collision realization and significant harm, showed 3.0 days. This metric, developed by researchers from the Outer Space Institute, estimates the expected time until a potential collision of objects in low Earth orbit in the event that satellite operators stop evasion maneuvers. In January 2018, the value was 164 days. In June 2025, 5.5 days. 3 days is a reaction time that is shrinking rapidly as the number of objects in orbit grows. And solar activity heats the upper atmosphere, changing the aerodynamic drag experienced by satellites, and making their trajectories less predictable precisely when forecast accuracy is critically important. A catastrophic collision in orbit is not the loss of a single satellite. It is a cloud of debris that increases the probability of secondary and tertiary collisions. A slow chain reaction behind what is called the Kessler syndrome. The chain reaction in orbit develops slowly, but the solar activity capable of launching it continues right now, and the declining phase of cycle 25 turns out to be no less unpredictable than its rise. By June 2026, the sun is formally in a decline phase. The smoothed sunspot number began to decrease from the peak values recorded in 2024. Forecast models show an average annual sunspot number for 2026 of around 85, a noticeable drop compared to 150.6 in 2024. But here is what draws attention. The standard forecast error for 2026 is 13.51, more than twice as high as for 2025. Uncertainty does not decrease along with activity. It grows. Models are still not sure what the sun will do next, and data from the first months of the year confirm this uncertainty. The February series of X-flares from region 4366 occurred already during a period when activity under all baseline scenarios should have been steadily declining. The NOAA Space Weather Prediction Center notes, "Solar maximum is not a moment, but a phase that can last years." When scientists define the quote-unquote absolute maximum, they mean the moment of the reversal of the sun's magnetic field, the point after which half of the maximum phase is still ahead. As of the time of recording this episode, data from recent months are insufficient for an unambiguous determination of whether this point has been passed. On June 9th, 2026, literally yesterday, the GOES 19 observatory recorded a large coronal hole in a geoeffective position on the solar disk. A coronal hole is an area where the sun's magnetic field lines do not close back to the surface, but go out into interplanetary space, forming a stream of fast solar wind. When such a region finds itself in a position directed at Earth, the stream of accelerated particles reaches our planet in 2 to 3 days. According to current estimates, the fast solar wind from this coronal hole will begin to arrive at Earth around June 11th. The forecast is unsettled to active geomagnetic conditions. Aurora observers at high latitudes are advised to remain ready. In parallel, active region 4464 demonstrates increasing magnetic complexity. NOAA estimates the probability of an X-class flare from this region at 10%, seemingly a low figure, but in the context of a year when each month brought events that went beyond forecasts, 10% is not a comforting statistic, but a reminder that probability and inevitability are different things. But the former has a property of turning into the latter with a sufficient number of attempts. There's another element that rarely gets into public discussion. Most of the satellites providing early warning of geomagnetic storms, those few hours that allow power grid operators to reduce the load before the arrival of the shockwave, operate significantly longer than their planned mission lifespan. These devices are located at the Lagrange point alone, approximately 1.5 million kilometers from Earth in the direction of the sun. They are the only line of early detection between us and an approaching CME. When, in January, the ESA models predicted an ejection speed of 1,400 kilometers per second, and the real speed turned out to be 1,700, the difference of 300 kilometers per second meant that the shock wave arrived several hours ahead of the calculated time. For a power grid operator who relied on a certain time window for preparation, these hours are not an abstraction. The correlation between aging warning systems and the growth of unpredictability in solar activity does not mean a causal relationship, but it means that the question is worth asking. The question is worth asking, and not only about early warning satellites. If one steps back from the details and looks at the map as a whole, a contour emerges that none of the individual stories told above shows by itself. Here is what we know at the time of recording this episode. Solar Cycle 25, which an international panel of leading specialists in solar physics assessed as probably weak comparable to the previous one, produced a peak number of sunspots almost twice as high as the forecast value. Out of more than 100 published forecasts, only 4 turned out to be correct. This is not a private error of a single model. This is a failure of the entire predictive infrastructure of a discipline that should provide the basis for planning space missions, calculating satellite lifespans, and assessing risks to power systems. In January 2026, this weak cycle produced an S4 level radiation storm for the first time in 23 years, with an intensity that exceeded the metrics of the Halloween storms of 2003, which, until that moment, remained the benchmark for extreme space weather. In February, a series of 5 X-class flares in 4 days from a single active region, including an X-class 8.1 flare, one of the strongest in 2 decades. And all this in a phase that, according to all models, should be declining. Simultaneously, the South Atlantic anomaly, the zone of Earth's weakened magnetic field, continues to expand and split into 2 lobes, one of which is migrating in the direction of Africa. In 11 years of satellite monitoring by the SWARM mission, the area of weakening has grown by an area comparable to half of Europe. Underneath the anomaly, regions of reverse polarity of the magnetic field have been discovered. Field lines that go back into the core instead of forming a protective dome. And it was precisely inside this zone during the January storm that a glow was recorded that standard models of auroral distribution do not provide for. The crash metric for orbital safety shrank from 164 days to 3 over 8 years. Solar activity heats the upper atmosphere and changes the ballistics of thousands of objects in low orbits at a moment when the density of orbital traffic is higher than ever in the history of space exploration. The cost of protecting the 1,000 most vulnerable transformers in the United States was estimated at $100 million. The upper limit of damage from a Carrington-level storm for the American power grid is $2.6 trillion. The ratio between the price of preparation and the price of consequences is 1 to 26,000. These numbers have been known since 2013. This is what makes the combination of these factors unusual. Not each of them individually, but their simultaneity. The sun is operating at a power that was not predicted. Earth's magnetic shield is weakening in a specific expanding zone. The orbital environment is compacted to a critical level. Early warning systems are operating beyond their design lifespan, and the models on which all planning relies, from flight routes to insurance reserves, have just demonstrated that they are not capable of predicting the behavior of our own star, even on the scale of a single cycle. No agency at the moment has issued a warning about an impending catastrophic event. Monitoring continues. Data is arriving. The interpretations and connections between events that sounded in this episode are analytics based on open sources, not a scientific consensus. But the data we see does not yet add up to a picture that can be called calm. The picture is not calm, and it is not complete. It continues to manifest in real time while you are listening to this. On June 11th, tomorrow, the fast solar wind from the coronal hole recorded by the GOES-19 observatory will begin to arrive at Earth. This is not an extreme event. This is background activity, the very activity that within a week cycle was supposed to be even quieter. Region 4464 continues to become more complex. A 10% probability of an X-class flare is 1 attempt out of 10. The sun makes such attempts every day. For up-to-date information on the geomagnetic situation and safety recommendations, one should refer to the NOAA Space Weather Prediction Center, ESA data, and local civil protection services. This is their job, and they are doing it. Our job is different. We read the signals, and here is what the signals say at the moment. 7 years ago, the best specialists in solar physics on the planet looked at the available data, 24 full cycles of sunspot observations, 7 cycles of radio flux, and came to a consensus. The cycle would be weak. They were not careless, they were not incompetent, they worked with the best models that existed, and the models turned out to be insufficient. Not because scientists made a mistake in calculations, but because the sun operates on timescales and in complexity modes that 24 data points are not capable of describing. We are used to thinking of the sun as a stable object, as a constant. It rises, it sets, it provides light and heat. But the sun is a thermonuclear reactor with a diameter of almost 1.5 million kilometers, in which convective plasma flows generate magnetic fields of monstrous force and complexity. We have been observing it systematically for a little over 150 years. We have been measuring its radiation from space for several decades. We are trying to predict its behavior based on a sample that any statistician would call unsuitable for reliable conclusions. And yet, everything is built on these forecasts. The lifespan of satellite constellations, insurance models for power grids, calculations of radiation doses for airliners' crews on polar routes, orbital safety assessments. The entire structure of our technological civilization, dependent on electricity and electronics, relies on the assumption that we understand our star well enough to prepare for what it might do. January of 2026 showed that we understand it worse than we thought. On January 18th, at 18 hours 9 minutes UTC, active region 4341 produced an X-class 1.9 flare. Not the most powerful, not the fastest. But it was followed by a coronal mass ejection that flew 300 kilometers per second faster than models calculated, and a radiation storm that exceeded a threshold that had not been reached for 23 years. The next ejection may be weaker, or it may be stronger. Models do not know this, and we do not either, for now. Monitoring continues.